Hey everybody, I was just going over my notes from today and I don't know about you, but I was really not happy with the way things went in class today. So I wanted to go over the compound interest problems specifically and show you how we actually developed those and why we had so much problem with the other equation, which was use the fractional exponents. And the reason why I was having so much trouble is because I was getting these two equations confused. So I want to just focus on the compound interest issue because I think that's more important and relevant to your life, and then later I'll make another recording that shows you when and why and how to use the other equation that included exponents with fractions in them. So let's just focus on just compound interest, and let's just talk about those equations specifically. So what we're going to do is we're going to start with the same functional equation that we had for all geometric models, and that's when we went over it in class today. You start with what you want to know is how much money am I going to make after a certain amount of time with a certain growth rate. So that's pretty easy because we've got our money in the bank that we've got here, right? And that's our B sub n. We have our initial investment, that money that we start off with, and that's B sub 0. We have a growth rate, but with compound interest, it's a special kind of growth rate, and we're going to explore that a little bit more detail. And then we have how many times that growth rate, that compound interest, is being compounded. So let's take a closer look first at just the growth rate. So going over the example that we went through in class, where if you have $100, you have a 10% interest rate, you multiply it by $100, you add it to that $100, and that's what you get. And so we kept running into this issue of the 1 plus a decimal point times our initial value. And that's how we always got that growth rate that was greater than 1. But when you're talking about compound interest and APRs and things like that, this sort of explains why you always have 1 plus that decimal, which is really a percentage expressed as a decimal, right? So 1 plus the percent change per period times our initial investment. So that we went over, and I think pretty much everybody has pretty strong on that one, so this should make sense to pretty much everybody. Now let's talk about APR, annual percentage rate, and that's in bold for a reason, because annual means per year. And what that means is that even though it's an APR and you're given, say, a 10% rate or a 12% rate or an 8% rate, you always have to divide it by how many times you're compounding in a single year. So that's why I made this new variable here called P, call it periods in a year. Now whether that's monthly compounding, then you divide by 12. If it's daily compounding, you divide by 365. If it is hourly compounding, you would divide by number of hours in a year, because you're always given an APR with these bank interest rates, and so you always have to divide by how often it's compounding. So this growth rate R that's in our geometric functional equation is actually going to be, for anything involving APR and money and interest rates, things like that, it's always going to be 1, which we proved up here by solving this equation, plus whatever our APR is divided by how often it's being compounded. So that's what we always have to do in order to find what that actual growth rate is for these bank rate types of equations. Alright, so now that we know how to construct our growth rate, the actual R, from all the pieces that were given in a problem like this, now we can take a look at that exponent part, right? So again, here's our original equation, B sub n equals our initial value times that growth rate, which we already explored. Now let's take a closer look at this n right here. So that's number of times it's being compounded. Now again, remember, it's an annual percentage rate, and then P is our periods in a year. So how many times it's being compounded is how often it's compounded, right, which is our P, we already defined that, times how many years we leave it there. So for example, if it's compounded monthly and you leave it for 1 year, then it's 12. If you compound it daily and it's compounded for 1 year, it's 365. If you compound it monthly and you leave it for a half of a year, so that T would be 1/2 times 12 months in a year, so it would be 6, or 6 months. Make sense? I hope so. Alright, so now let's put all these pieces together. So here was our original equation up here. B sub n, how much money we're going to have in the bank, is our initial investment times that growth rate, that funny growth rate that happens with APRs, which is 1 plus the APR divided by how often we compound it, raised to the power of n, which is t, the number of years that we're actually compounding it, times p, how many periods in a year that we're compounding. And so our actual equation of how we get this stuff is all right here. So, amount of money that we have after a certain period of time, so this should actually not be b sub n, but actually, let me fix that here, b sub t, right, is the initial value, how much money we put in the bank, times the funny growth rate, which is 1 plus the APR, divided by how many periods are in that year, because that's always an annual percentage rate, watch out for that A, raised to the power of t, the number of years that we leave it in the bank, times how often we compound it. And that is the equation that you use always when you're talking about compound interest. So that's not the same thing as that other equation with the growth rate with a fractional coefficient. We'll talk about that in a completely different video, so don't worry about it for now. But this should help you solve any problem that you run into when you're talking about APRs compounding. And it doesn't matter whether it's interest that you're earning in a savings account, for example, versus interest that you're paying to your credit card company. Doesn't matter, the totals always add up and they always use this formula. I hope this helps, and if you have any other questions, please always feel free to email me, call me, whatever you need. I promise I will do everything I can to help you understand. Alright, night.